Hey, let's talk about the invisible world that's all around us. I mean, the hidden forces that are literally holding everything together right now, from the chair you're sitting in to the tallest buildings on Earth. It's something we take for granted, but have you ever really stopped to wonder?
Really thought about it? What is actually stopping everything from just, well, falling down? It's a huge question, but the answer is so elegant, and it all starts with something incredibly simple.
Yup, we're going to build this entire idea on just one single, ordinary wooden plank. Seriously, this one simple object holds all the secrets we need to unlock the principles that let us build massive, world-changing structures.
Go ahead and picture it. You step right into the middle of a plank laid across a small gap. You feel it bend a little under your weight, but it holds you. What on earth is happening deep inside the fibers of that wood? What's creating the force to hold you up? That's the mystery we're about to solve.
Okay, to understand that internal battle, we need to meet the two main players in this whole story, stress and strain. You can think of them as the basic language that all materials use to talk about force.
So when you stand on that plank, you're the external force. Stress is what the plank does in response. It's the material on a molecular level pushing back, resisting your weight, basically screaming, "You're not going to break me." It's a measure of that internal fight.
And here's how we calculate it. See, stress isn't just about the total force. It's about how spread out that force is. Think about it. Pushing on something with the tip of a pencil creates a ton of stress in that one tiny spot. But pushing with the same force using the palm of your hand, the stress is way lower because it's spread over a bigger area.
Now that internal fight, that stress, doesn't happen for free. The consequence of all that pushing back is strain. Strain is the physical change you can see. It's the bend, the stretch, the squish. It's the physical evidence that a battle is being fought inside the material.
And we measure strain as a percentage, really. It's not just it stretched 1 millimeter. It's how much did it stretch compared to its original size. This is super useful because it lets us compare how stretchy different materials are, no matter how big or small the piece is.
So what's the connection between these two? Well, a brilliant guy named Robert Hooke figured this out. His rule, Hooke's law, basically says that for most materials, the harder you pull, that's stress, the more it stretches, that's strain. It's a really simple, direct relationship. More fight equals more stretch.
Okay, so let's bring all this back to our plank. We know it's feeling stress, and it's showing strain. But what kind of fight is actually going on inside that wood as it bends? It turns out it's not just one thing. It's two opposite things happening at the exact same time. Just think about the shape for a second. The plank is curving downwards, like a frown. What does that do to the wood fibers at the very top of the plank? And what about the ones at the very bottom? One side is being stretched, the other is being squeezed. But which is which? And here's the answer. The top fibers are being squished together. We call that compression. Meanwhile, the bottom fibers are being pulled apart and stretched out, and we call that tension. And this, right here, is why engineers choose specific materials for specific jobs. Concrete, for example, is an absolute beast at handling compression. But steel is the undisputed champion of tension.
Okay, this brings us to what is, for me, the absolute coolest part of all of this. We all know this intuitively, right? A ruler is super easy to bend when it's flat, but try bending it on its thin edge, it's way harder. But why? It's the same material. The secret isn't in what it's made of, it's in the shape.
And the concept that explains this magic is called the moment of inertia. Now, I know, that sounds super complicated and intimidating. Don't worry about the name. All it means is that some shapes are just naturally better at fighting off bending than others. It's a shape's geometric superpower. Okay, let's look at the formula for a simple rectangle like our plank. I is that superpower we were talking about. B is the width of the plank, and D is its depth or height. Now look very closely at that formula. One of those letters has a ridiculously huge impact compared to the other.
So here's the million-dollar question. If we take our plank that's lying flat and we flip it up on its edge, we've just doubled its depth. How much stronger did we just make it? Did we make it twice as strong, 4 times stronger, or, get this, a crazy 8 times stronger? The answer's right there in that little tiny number 3. The depth is cubed. This means when you double the depth, its resistance to bending goes up by 2 cubed, which is 8 times. This exponential power is probably the most important secret in all of structural design. It's why I-beams are shaped like an eye. It's all about putting material as far away from the center as possible to make that D value huge.
So we've spent all this time talking about how things stay up. but understanding how they fail is just as important. Let's switch gears and look at a column, something that's designed to be squished, to resist compression.
How a column fails totally depends on how slender it is. If you have a short, beefy column, it's really good at resisting bending. So if it fails, it's just going to be literally crushed by the weight. But a long, skinny column is a different story. Its weakness is bending. Long before the material itself gets crushed, the whole column will suddenly bow out to the side in a dramatic pop. That's called buckling.
And there you have it. We've come full circle, from the internal tug-of-war between stress and strain to the battle of tension versus compression and that geometric magic of the moment of inertia. These exact same ideas, just scaled up, are what allow us to build the incredible skyscrapers that define our cities.
So, next time you're out and about, crossing a bridge, or just looking up at an office building, you'll be in on the secret. You won't just see steel and concrete, you'll see a hidden battle against tension and compression. A structure perfectly optimized by the unbelievable power of its shape. Now that you know the secret of the D-cubed, what are you going to see differently?